Okay, so here's what we have. Yesterday we studied just the neural network, the code which is responsible for binary classification on a certain condition. Today we come to something called a recurrent neural network. So the term recurrent relates to remembering. Okay, it relates to a bit of the past because it has to reoccur. I mean, things are reoccurring. Things are reoccurring. So you want, where is this usually seen? To understand recurrent neural networks, the context of time series data is most relevant. So what's happening here? Okay. So what's happening here is you're trying to predict, or this is just a data set in front of you, and let's say time series data. You have stock market data. Now, usually stock market data, time series data, all these are very unreliable in terms of prediction. Why one would think of that it is unreliable in terms of prediction? Because time series data, as usual, it has time over here. Then there are certain values, the stock prices are moving like this. So what we are trying to do is, I mean, the whole stock market data that we collect, and we try to do day trading, we try to do long term trading, all that thing that people are doing. The basic fundamental flaw in it is we feel that causality or cause and effect, for to explain the causality, you are supposed to have different parameters for it. For example, the causality of the price rise, does it depend on, is it really depending on time, or does it depend on geopolitical issues, on economy, on weather? So many other stuffs actually affect the price. But we, in time series data and stock market data, we say one target vector is affected by the feature vector, which itself is time, which is a wrong way of doing it. So never do this. Never try to predict based out of this. But nevertheless, if this is the way you have to do it, then how recurrent neural network will help? One, you can see the overall price, and you can say, you want to say at this particular time what will be the price expected. Learn what will be the price expected by looking at the pattern of the data, which is from the past. Now, recurrent, instead of directly using this as a linear regression problem and trying to, you know, fit a line across this, that will not give you the actual, that is not the right way to do, because in stock market and time series data you don't do this. This is purely a different set of problem statement. This is not linear regression that you're trying to do. Okay, we are trying to establish the occurrence of this. For example, you see here basically how recurrent neural networks actual implementation works. Use this value to get this value. then use this value to get this, then use this to get this. So this is how you want your neural network to remember it. Okay, so you want it to have a recurrence nature to it. So it says, if I'm here today, build the relationship in such a way that I'm here today because of this point, and here it came because of this, and this happened because of this. So build a relationship moving backwards. Correct. So that, if you set that kind of a relationship, so it looks something like this. If you want to set up a neural network, it looks like this. See this here? Put this input here, get this here, and then take that value to the next layer. To get this, you have to put this as the input and get the value. But there is a connection. There is a connection here. You see this input value which you have taken, you are going to multiply it by some weight, and of course this is a bias. Everything remains same. We don't keep on changing the weights, we don't keep on changing the bias. This is set. Only thing that changes is the value goes from here and gets summed up here, then this value goes from here, gets summed up here, then this value goes from here, gets summed up here, and finally you get the, of course you have all these dots here. Okay, because equal number of weights and biases are added, as many number of points are there, that many number of weights and biases are added. This is your expectation. This is how your recurrent neural network works. So all these data is added sequentially. First this layer is computed, then when you compute the next layer, you take this value, and this value's prediction is here added to this. Then the third prediction comes up. While taking the third value, see, one, you take the real value, then you take the possible prediction of these two. There is a predicted here, and there is a okay. So there is a predicted value out of because of these, and then there's a real value. So the predicted value here at this point of time is added with real value. What predicted, what real, together they have to predict the next. Till here, don't try to predict this only by this. I hope you're understanding. This point's prediction, this particular point's prediction, this, okay, this prediction, this, oh, just hold on. I think I have a lot of applications running, so I think I'm having. Yeah, are we back? Are you able to hear me?
Yes, sir.
Yeah.
Yes, sir.
So the point I'm trying to make is this particular point here. This particular point, if you want to predict this, don't just try to predict it based on this. The prediction of this should be a function of both this, the actual value preceding it, and what these two, when you use these two as a projection, this plus this should give you this. Then if you want to predict this and this will give a projection here. No, that plus its original should give you this. So that is the nature of recurrence. So every time you are adding biases and weights and for this projection and then this real value, then again bias and weights for it, the same bias and weight will continue. You are not looking at different biases. You are setting up the problem with same bias, same 2.2. For example, I've taken 2.2 0.414 here. So you take it through this activation function, you get a new value, that you bring it here, the actual value into weight plus this bias into this new weight, which is actually the input from the previous prediction. This is the nature of recurrence. Okay, it'll take some time. You have to. That's the reason why I'm recording it. And that's the reason why you get the recording so that you understand. But what is the problem? Recurrent network. If you work like this, what happens? This is recurrent neural network, but there is a problem with it. Okay, that problem is called the vanishing or exploding gradient problem. So what happens is, see all these weights that you are adding to the next network. This weight is getting multiplied, right? This multiplied, then again multiplied. This gets multiplied by this. This again gets multiplied by this. This again gets multiplied. This again gets multiplied. Think what happens. You have two problems. One is vanishing. One is exploding gradient. Right? You have two problems. So let's just consider the weights W1, W2, W3, W4, and ignore all other biases and other weights, right? So remember how the optimal parameters were being calculated earlier. So the optimal parameters you would calculate by taking the chain rule, right? You would get that slope value by using the
Just one doubt.
yeah.
Okay, so the output from the previous stage is fed into the next stage, right? So, I mean, why are we saying it is getting multiplied? We have just added it, right?
No, it's not added. We are multiplying this into there is a this is this one, this whatever the output is here, we actually multiply this by another weight W2 and then add it.
Okay.
Okay, it will come later. So I just wanted to show you first
Okay.
that somehow this one affects this is what I wanted to show you. Okay, this
Right.
is affecting this is affecting this. So that is what I wanted to show you. So here, this is much more clearer when it comes to see here. Okay, this is where everything would have been clear. So basically, if you want to see how the weights 1 is affecting the sum of squared residuals, how this effect will come about by saying how W1 affects X2, how weight 1 affects the formation of X2, but this you will get how W1 is affecting X2 depends on how X2 is affecting Y2 and how Y2 is affecting the predicted and then how a predicted is affecting the SSR. So this is how you will set up the long chain
Okay.
rule. Correct. So this is how you will find it, and as big the network is, that is how you will find the optimum value by finding that slope at that, and you will have different slopes here, and you will get some value optimal parameters. Usually here, I think this is the global minimum. You are expecting this value. If you get that, you are finding for that particular step the slope, and then you put it back, and eventually you gradient down to this value. This is where your the minimum thing happens. So basically that's what we say when you're trying to minimize the loss function and the sum of squared residuals. So far, is it clear? Again, if you want, the problem is time series data. In time series data, you want to predict stock price of a few days later. Always it is a tomorrow. But let's say this is the tomorrow that matters to you. Okay. But you know that it depends. This the value, should it just, are you okay for it to be a generalized version of a straight line? Are you okay because your stock market data looks something like this?
Correct.
So if you just generalize it by this
No,
or generalize it by this, will you be okay with it? Because it's the
no,
money you're putting, no? So you want the best of the best possible prediction. It turns out recurrent neural network is very good at it. How it is good at it? Because I am not only trying to use the previous data to get to this, I am trying to use how the previous to previous data affected it. In this, I'm also
no,
trying to say not just how the previous data, I'm saying how the previous data's prediction of the day before or the days before it predicted plus what it is together, I'm predicting the new data. So if I'm not, I can't just rely on predicting this directly. My network should be able to predict this, then this, then this. I should be able to explain the entire curve. This is not just one curve fit.
no,
This is state prediction of each state. Your entire recurrent neural network should be able to account for each of these points as a function of the previous state,
correct.
right? So that is what your recurrent neural network does, and you can sort of now get intuitive idea that it is more stronger. It's a much stronger case, correct, to expect. However, the problem with this particular connection, the way we are connecting here, W2 into this, and then W2 to this, W2 to this. The problem with this is that you, let's suppose you set a weight greater than 1. Okay, you're here. You start with a weight greater than 1. Suppose your weight is 2. So, what is this equivalent to? This something into 2 plus this, into 2 plus this, into 2 in. So basically your IP1 in general you're multiplying it by 2 into 2 into 2 into 2 only, right?
Correct.
Removing all other stuff, algebraically separating all other stuff, you're ending up with this only, correct? So you are looking at 2 into 4, 2 raised to 4. That is just for 4 points. 1, 2, 3, just 4 for 4 days earlier data to predict the fifth day. You're already looking at, in case your weight just got initialized to above 1, you're looking at 2 raised to 4. So if you have 50, 100 days, what will you do? Basically, this is, it will be raised to the number of feedbacks that you have. And number of feedbacks depends on number of past data points. Where is that? Right? Number of past data points. That's what it depends on. Fine so far?
Yes.
So if you do this for 50 days, you're looking at gradients exploding. Because suppose you want to calculate the slope at this point, it is nothing but your x1 is nothing but a w1 into w, the weight raised to 50 with respect to your w1, where x1 is this. So now what is the problem? It is too big. This number will be too big to expect those small step sizes, which is going to lead to optimal weights. It will overshoot because of the gradients itself are so large that you will just, it will just be too big a step and you will never get the optimal parameters. Now this, see, this you are able to, if at all you are able to understand this, you are able to understand this because we did the previous example properly. Because the memory of the previous example is still there in front of you, correct? Yes, right?
Can we go back to this right above the network? Okay, so the meaning of this line too big to expect a small step size is like
This number
ingredient.
is going to be too big to expect small step sizes.
Basically, what we okay, I'm just uh, reiterating this in language, right? So
Wait,
it is
wait.
so big, right? We will
I'll
never
show
be
you. Wait,
able to
I'll show
achieve
you.
a small step higher than gradient descent.
I'll show you what it means. Wait. You remember this step size?
Yes, sir. Yes, sir.
You step size you got by slope into learning rate.
Right,
No matter how much you keep the learning rate, if the slope itself is too much,
right,
correct? How you got the slope? By this now.
right. Derivative.
DSSR by DB3, correct?
Right,
Now,
right,
if that big number comes up here, the step size becomes too big. So the new bias that
right,
is being used, or the new weights that is being used, will also be very huge.
right.
So how will you come to that slow step parameters? Like slowly you have to increase, right? Slowly you have to decrease, slowly you have to decrease, slowly you have to decrease.
Right,
Otherwise, operate from here to here, directly from here to here, you will jump. From
right,
here to
right,
here, you will jump. You
right,
will come here only when you come slowly, right?
right.
So if
Agree.
that is what is that is the meaning of
Hmm.
W, this particular W2 weight raised to 50 in recurrent neural networks. See, recurrence is important, but the problem with recurrence is the exploding gradients. When you set weights greater than 1, so natural solution is weight should be less than 1, correct? Never take the weight, set the weights above 1. That should be the solution, correct?
That will make it very small, right?
Correct. So if you limit that weight 2 which is there to be less than 1, now this results in vanishing gradient problem. Check this. Zero point 0.2 will be greater than zero point 0.2 the whole square. Will in turn be greater than zero point 0.2 the whole to the whole cube. Will in turn be greater than zero point 0.2 the whole raised to 4. So now what we do is we end up taking steps that are too small,
So small, but
and you will never get to that. This you can't, you don't see this in 4 or 5 data points or 10, 15 data points. When you have like 200, 300 data points to look back and then predict, because that's what you need, the prediction pattern, correct?
right.
For that you need, you'll get stuck over here. So now the
Agree.
solution for it is, I'll not explain this fully because it tomorrow when I explain and do the project it's going to, but I'll connect you with long short term memory now, the intuition of it, okay? Because
Okay.
you can't just. So what was happening? The problem that was happening is that these W2s are connected to each other and it is getting multiplied. This one is getting multiplied by this and this one is again getting multiplied by this. So somehow we want a network wherein, okay, you want a network which does something like this. Okay, so see here. So let's visit the problem back. To
Oh,
predict this, to predict this point, you we had to predict this. To
right.
predict this point, we had to predict this. Correct?
Right.
To predict this point, we were predicting this. Now to predict this point, we are predicting this. That's how. So finally, using this, we want to predict this, and so on. That's how we are going long. Okay, so longer you go back, the more problem you have when the gradients multiply. What if we take a combination of the long memory and the short memory. So we need to have a gate which is going to be something like, see, one line and the second line. There will be a series of short memories. Short memories means short, just 4 points previous. Okay?
Okay. Okay.
Series of short memories which are sequentially affecting and telling what should be remembered in the long term. Means how much of the long term points are you supposed to remember? Not all. But what are the
Okay.
most effective long term memory points needs to be remembered. Because sometimes the states are so close to each other that we would rather average all these. You see this? And make it one, correct?
Okay.
If I average this, I get only 1 point. So I just want to remember this. Then if I take an average of this, it just becomes 1 point. So on an average, how much would I like to remember is I'll take a series of short memories which covers the long memory. So that's the long short term memory.
Okay.
Okay. This is the foundation for your context and all this. So here you see. Here, see? So here what is happening? You're still multiplying by a weight and still adding. But it is only one weight and one sum that gets added. Not recurrent again and again. Here, for each of this section of the short term memories, the short term memories have all these weights. But eventually they'll all come together and represent itself as just one. The small ones gets averaged. Okay, and we can define how short this window can be so that we get away from or negotiate ourselves between not get trapped with the vanishing gradient problem. So that's how we are trying to see this whole picture. Now this I'll explain tomorrow. So hope you have understood how we came from recurring neural network to long short term memory. Okay, so I'll share this video. You have to watch it. You have to understand it. That's why I don't want to go too fast. You need some time to go through this. The gist of this is, earlier we used to have this loop back in, loop back in, loop back in. Now we don't want that. The whole looping, there is no loop at all. There is just these short terms which are predicted and then given to this, and they are just linear in nature. There is no looping effect here. More clarity on this, I'll give you with an example. But for today,
So,
just yeah,
it's like let's say earlier we had 10 data points. So because of 10 data points, we were facing those problems of vanishing or exploding gradient. So what we said, okay, let's take an average of 3 data points. So eventually we will be left with just 3 data points that reflect the whole 10 data points.
yes.
So use those 3 data points.
So basically, wait, I'll put another. To predict this,
Okay.
to predict this, you use this to predict this. Okay. Now to predict this, you will use this and this prediction
Right.
together to predict this. Correct?
Right.
Now
Right.
to predict this, you will use this plus the prediction of this. You will use this also, but you will also use this and this prediction. So three. By the time you
Right.
come to predict this fourth point, you need three. To predict this
Right.
fifth point, you need four. To predict
Oh,
this,
right.
so you see how it is. multiplying
And
it actually
multiply. Sorry.
exponentially increases to get this. See, and the perfect prediction happens, or almost very close to the happens, because you're taking it like this. But to set this problem up, you get the gradient problem. So
Right.
whatever factoring is happening here, no. So how much to remember? At this point of time, do you at let's say at this point of time, do you want to remember all seven, or how much of it that you want? How much is really long, or how much is really short? You need a filter. You need a setup to control, to to tweak how much is long. How long do you want to go back to predict that next
Okay.
point?
Okay.
Right. That tweak is given
Okay.
by this setup. So basically here is the percent long term to remember. How much percentage of the long term will you remember? And percent potential memory to remember. Right. This, of course, I'll explain this whole thing in a new setup, but I want you to just connect from recurrent to LSTM now. And you'll see here, you're not using that ReLU. Activation functions are here also, but you're not using ReLU. Here you're using a softmax, or sorry, this is a sigmoid, and this is -1 to 1 tan h. Okay, sigmoid is from what it does, fits the value between
0 to 1.
0 to 1. Tan h fits the value between -1 to 1. Okay, so we'll understand, okay, why here sigmoid, why tan h. All of this is, as I told you, nobody expect you to know all these internal depths. But fine, but so keep on appreciating till you go to later on, if you are going to go into transformers and Gen AI and everything, we'll have to put this perspective.
Okay.
Okay, so I'll not say
Okay.
much because it's getting recorded. I don't want this video to get confusing. You have to figure it out, and we'll come tomorrow. And if you have doubts, we'll clear it. So far, this is the meaning of it. Watch it again, and you'll get the point. Okay, let me just
Sure, sir.